All right, so we carry forward in kinematics and we go on to lesson 6, which is kinematics involving acceleration with displacement. So here's one thing I want to point out right away. In lesson 5, what we talked about is acceleration involving velocities, time, and the overall acceleration magnitude. So that actually gave rise to this equation right here. And so we established a bunch of problems using that equation, and we manipulated that equation. We found things like initial velocity, final velocity, time, maybe just as simple as finding acceleration. But now what we're going to do is we're going to expand our definition of calculating acceleration, and it's going to involve things that have displacement. So we now have one equation, two equation, and three equations to add to our mix that we've already established. So let's continue forward with this. Now, the kinematics formula we've learned thus far, one we have that represents our uniform motion is the following. It's our velocity equation, or velocity equals displacement over time, or speed equals distance over time. So we can think about it in terms of a scalar or a vector quantity, and this gave rise to the uniform motion equation. So we only have one equation that matches up with that. Then what we did in lesson 5 is we established this new acceleration equation where we have acceleration is the change in velocity over change in time. And one thing I would like you to add here before I comment any further on this is I want you to add the vector symbol above these two velocities, indicating that these have directional magnitudes, which is really key. Now, this formula was used when we had accelerated motion. So highlight and put that together when we're not looking to calculate distance and displacement, but rather we have velocities and we want to calculate the overall acceleration, or we have acceleration in time, we want to figure out a specific velocity. This was our equation that was our basic first accelerated equation. Now, again, just like we said on the first page, what we're going to do is expand our definition of this and actually add a couple more equations, which may complicate things just slightly, but realistically, it's not going to overcomplicate it in the sense of it's not going to require any more effort, as it's going to require just more organization overall. So let's see how this looks. Now, the kinematic formula we're adding today, as you can see with these, they all involve displacement. Now, just like we did on the previous page, when it comes to some sort of vector equation, I want you to add tails on these to indicate that these are directional magnitudes, or they are vector quantities here. So you can add tail, tail, tail. The only one that I don't want you adding anything onto is this one here. Now, when we get to the examples that involve this, I'll explain it then. But for now, we just want to see this one and be like, I'm going to leave the tails off of that, because on your formula sheet, they'll put vector symbols on these equations. But when it comes to the number 5 one, you see it without, and there's a specific reason why. So we're just going to hold on to them without it. Now, with these, an important note to make is that we do not have to memorize these. These actually all appear on the formula sheet. And so if you just want to quickly note that to yourself is, hey, if I know that these are going to be on the formula sheet, do I need to sit down and spend hours memorizing these things? No, because you'll always have that formula sheet out in front of you. You just need to know how to apply these. Now, again, these formulas are all used for when we're calculating accelerated motion, but on top of that, when we're looking to calculate the distance or displacement during that period. So clearly, if they involve the d value or d variable here, you're not just looking for velocities, times, or acceleration. You're now expanding upon that definition a little bit. Okay, now when we solve problems that involve these, because now we have this mix or this array of equations, what we now have to look at is say, there is going to be certain variables that matter, certain that don't, and then certain ones that we're looking for. And so here's what you need to start and make sure that you always remember. This format holds true no matter what. No matter what problem type you're doing, you're always going to list out your 5 variables. So you're going to have displacement, velocity, acceleration, and time. And just to really re-emphasize this, when we're looking at these are directional magnitudes, so I want to make sure they have the vector tails on them. And here's the following process that you want to start. You are going to know 3 of these variables. In every question, you'll at least know 3 things. You're going to have one that you don't know, and that's the one that they're going to ask about. That's the whole point of solving the question, is that you're trying to figure out what you don't know. And then there's going to be one, which I even recommend you highlight this in here. There's going to be one variable you just don't care about. So out of these 5, you're going to be like, hey, maybe it's an acceleration equation, but they don't mention anything revolving around the displacement. Well, I want you to just put a little X there and be like, yeah, this doesn't matter for the equation. And you'll see what we mean going forward. But here is the following format we'll always follow. List out those variables, and then we're going to figure out 3 that are known, 1 unknown, and then 1 that we just don't care about. Now, continuing with the assumptions, this is very critical because this helps you identify which variables you know and which ones you don't. What we're going to look at is if an object is dropped vertically, we're going to say that its initial velocity, or VI, is equal to 0 meters per second. If they say dropped, it's like me holding it out horizontally and then just letting go. So clearly that starts at 0. If an object is thrown vertically downwards, key word is the thrown vertically. We now need to realize that our VI is not equal to 0. It has some sort of overall magnitude that would most likely be given. So we cannot assume if something's being thrown that it starts at 0. If an object starts at rest, that's another way of basically saying dropped. So what we want to do is say VI is equal to 0 meters per second. Perfect. On the vertical plane, the final velocity really means the velocity right before it hits the ground. So I want you to say VF is the velocity right before the ground. And make sure I don't erase. There we go. Excellent. There we go. On a vertical plane, the acceleration is always, okay, so we're going to put in A is equal to, well, if it's in the vertical plane, we're always going to say that this object is in free fall unless it's being acted on by some external force. But in this case, it's not going to be acted on. These objects are just going to be free falling throughout space. So we're just going to say this is negative 9.81. And for many of you, you're probably like, oh, that value looks familiar. It's also equal to the gravity of Earth. Close to the surface, that is, because as we go forward, you're actually going to see that we can change that g value, but the acceleration as it's close to the surface is just negative 9.81. And don't get this negative tripped up with speeding up or slowing down. Remember, when we talk about vector quantities, the magnitude determines if it speeds up or slows down in combination with the direction. And so this direction just means it's going down. The magnitude is how much it's going down by. Okay, on the vertical plane, if an object is dropped or thrown downwards, the displacement and the final velocity are both negative. And the reason is because they're both heading in the downwards direction. And so what I'm going to do is I'm just going to put in negative here for indicating that that's the answer. Negative, or in brackets, negative symbol. And the reason is because in vertical problems, we always set up our axis in the following way. We have arrows pointing up and down. We say positive is up, negative is down. And thus, if both of those things end in the downwards direction and they're both heading towards the surface of Earth or in the downwards direction, we're going to both assume that they are negative. So these assumptions are very critical for us because throughout the sentence, they might not say, oh, VI is 0, but they might be indicating that through the words they say. Or they might be talking about acceleration of an object as it's going through the air, and you have to recognize it's always negative 9.81. Okay, now here's the table that you can use. So if we're going through these problems and we want to list out these variables that we want to know and don't know, you can list them in a horizontal table like this. For how I solve them, I always put them just in a vertical stack. So whether you want to write them like this or you want to write them in a vertical stack, either way, and I'll show you what I mean just before we actually tackle some problems and move forward. I typically write it as displacement, VI, VF, acceleration, and change in time. And I'll say equals, 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 and I'll have even my vector tails on there. But that's typically how I write it. And then I make sure that I just include the values next to those as it looks. So horizontal, vertical, whatever you prefer. All right, now the rest of the steps, we'll read through them, but realistically, I think we can actually tackle this in a fewer step type of approach, but we'll read through them. Once you've made your table, choose the proper equation. So we go to our formula sheet and we make sure it matches up to the description. Rearrange it if necessary. So if we're solving for one variable versus another, solve and add the units, making sure that we have directional signs and we have our units attached to every number. If you're dealing with a vector quantity, make sure you add direction, aka the positive or negative, or up or down, whatever you want. And then lastly, circle or box your answer just to make sure it's all obvious for us. So they've listed out about 8 steps, but realistically, I think we can condense this down into maybe 1 to 2 to 3 steps just so we can see it all together. Okay, let's take a look at this first example here. A car starting from rest. Oh, they used one of those keywords. If I see starting from rest, I want to put 0 meters per second, and I want to highlight that piece. From rest. Really key word here, 0 meters per second. It accelerates at positive 5 meters per second squared for an unknown time interval, so they don't give us any time. If the car travels 250 meters in the acceleration period, what is the time interval? Okay, so what we want to do is we want to make sure we list out our variables here. And so I'm going to go to the vertical stack that I typically use here and list out the variables I have. So off to the left here, I'm going to start by saying VI, VF, acceleration, change in time, or even change in displacement, and then change in time. It doesn't really matter in which the order you put these variables, you just have to make sure you include them all and then put the magnitudes for the ones that you have. So starting from rest, 0 meters per second. They said acceleration was positive 5 meters per second, so I'm gonna make sure I include that, positive 5 meters per second squared. It's covered over a distance of 250 meters. The change in time, they didn't really refer to it, but they had said right at the end, what is the time interval? So we're going to put a question mark. The one that we don't care about here is VF. And so just as an exemplar of what I do when I don't care about the variable, I can just put a circle with a line through it indicating like, is that really going to have any payoff for us? No, we don't really need to worry about that. So I'm just going to leave that out. Now here comes the next part. So if I consider this to be step number 1, which is putting together my variables, step number 2 is going to be selecting the right formula. And so when I select the right formula, I look through the formula sheet and I'm like, hey, which one has displacement, initial velocity, time, and acceleration? And you should see that its displacement is equal to VIT plus the 1/2 acceleration times time squared. Now, a really nice, beautiful thing about this equation as it is because we have the VI is equal to 0, this piece cancels out because anything times 0 just wipes out. Now I'm going to be given displacement is equal to 1/2 acceleration times squared. We're solving for that time, so I'm going to multiply both sides by 2 to get rid of the 2 out of the denominator. That's going to give me 2 times the displacement is equal to acceleration times squared. And then I'm going to do kind of a 2-for-1 combo here. What I'm going to do is I'm going to divide by the acceleration, and this should have an acceleration tail on it like this. So I'll even go back here and just, probably a little too much on the eraser there. I'm going to make sure I go back and just get that out of there and fix that to be black just so it matches. There we go. So we're going to divide by the acceleration, and then I'm going to square root both sides because I have to get rid of the square root that is on the t squared. So this is going to give me the following. Time is equal to the square root of, and I should probably make sure I have my divided by my acceleration over here as well. There we go. This is going to be 2 times the displacement divided by the acceleration. Now what we're going to do is we're going to plug in the values here and then summarize our answer. So plugging in the answer here, I'm going to get this is equal to the square root of, in the brackets here, we have 2 times 250 meters. I'm making sure to include the magnitude and the units, divided by, if we had a positive acceleration, I should definitely have the positive there, 5 meters per second, squared, in the brackets, close it off, make sure my radical extends out. Now, if you do the math here, you end up getting an answer of, therefore, the time is equal to the acceleration period lasts 10.0 seconds. And that's your answer here. And so I'll make sure to highlight that, or you could box it, or you could bold it, or whatever you want there, but that would be the correct step here. Now, if you're one of these people that needs to algebraically separate everything, don't just try to combine steps like I did here. I only combine them just to save just a little bit of time there. But if you cannot see how I went from AT squared all into one step to get to here, just do it one operation at a time and that will be totally fine. Okay, so if the car travels the 250 meters in the acceleration period, it takes the car 10 seconds to go from rest up into that 250 meters. Now, they could have asked us for velocity final or something else here, but they only asked us for time, so we're good. Okay, so there's our following problem. You can clearly see that if we have problems like this, we can actually summarize it in 2 steps. List your variables, put in your equation, substitute everything in, and then you're good to go. Now, let's try out another example here. Example number 2. Again, we're going to make our vertical stack of our variables. So I'm going to zoom in here and go, step number 1, let's dissect the problem and pull apart all the variables. So maybe I'll just list out all my variables, and then as we pick them out from the problem, we can just add them to our list here. And so change in displacement, this is equal, this is equal, this is equal, equal, and one more equals. Perfect. Okay, we got our vertical stack. A car is traveling east at 30 meters per second, and it applies the brakes to generate an acceleration of 4.0 meters per second squared. Okay, I want to pull this apart a little bit. If we are traveling east, we need to recognize that the east direction actually means that this object is traveling in the positive direction according to our orientation. If they then apply the brakes, this is really important. They apply the brakes to generate an acceleration. Well, applying the brakes means that the acceleration is going the opposite direction. And so realistically, applying the brakes, I'm going to just put an arrow to this, is saying that we are going in the negative direction or opposite of the direction we're traveling. If the final velocity of the car is 5 meters per second east, again, this is going to be positive, what was the displacement of the car during the acceleration period? Okay, so let's write everything out here. I'm going to write out VI as positive 30.0 meters per second. And the reason I'm writing positive instead of east is because we can assign a sign to this as long as we have an axis. So realistically, maybe it would be even a good idea to do this above here. When we talk about this specific problem, we have the following here. We have something that is west, which is the negative direction, versus east, which is the positive direction. And as long as we have this axis written out here, then using positives and negatives is fine. Now, the final velocity here was positive 5 because it's still going in the east direction, but it's just at a less magnitude. The acceleration was negative 4.00 because it's going in the opposite direction, or the brakes are being applied, meaning the car is slowing down. And then the change in time didn't really matter to us. They never mentioned anything about a change in time. What they did ask for, though, was what was the displacement over this period. So now what we need to do is we need to write an equation that is symbolic of these variables where we know the first three, we don't know the time, or we don't care about the time, and then we're trying to figure out the displacement. And what you should pick out from your formula sheet for number 2 is that we get velocity final squared is equal to velocity initial squared plus 2 times the acceleration times the displacement. Now, again, this is that one equation that doesn't have the vector symbols on it, and we can actually explain it in this problem, or maybe even a little bit later, because I don't think this one quite shows why yet. So we're gonna hold on to that idea that this one doesn't have vector tails yet, and then we'll get there. Now, we want to isolate for the displacement, so I'm going to subtract away VI squared from both sides. When I subtract away VI from both sides, I get VF squared minus VI squared is equal to positive 2AD. Now what I need to do in order to isolate the displacement is I'm going to divide by 2 times the acceleration to both sides. When I divide by 2 times the acceleration to both sides, I end up getting VF squared minus VI squared divided by the 2A is equal to displacement. Now we want to start plugging in the values. So what I'm going to do is just put the D on the left-hand side here and then plug everything in. So my final velocity was positive 5.00 meters per second, and this is squared, minus the positive 30.0 meters per second squared on the outside like this, because we're not talking about acceleration, we're talking about the squared of the actual velocity, divided by 2 times the acceleration, which was negative 4.00 meters per second squared, and the squared goes in the brackets with the S because we're talking about acceleration. All right, now to summarize the solution here, let's see if I have any room off to this side here. It doesn't look like it. So what I'm going to do is maybe just go off to the left-hand side here in that white space, and we'll summarize it. Therefore, the displacement for this problem is equal to, you plug this all into your calculator, and I want you to logically think about this for a second, and just like maybe pause the video for like 10 seconds just to think about this. If I gave you a problem where somebody is driving in the east direction, they slowed down but are still ending up in the east direction, should I then get a positive or negative displacement? Now, the answer should be that you get a positive displacement and the magnitude is 109. Or we could say that the answer is displacement is equal to 109 meters in the east direction. Remember that you may be given either or, that either answer could appear on any sort of quiz, assessment, test, whatever it might be, because they are both synonymous to each other. Positive and east can both be correlated as going in the same direction there. So you may see either or in terms of an answer. And again, what do we see out of this type of problem? We see a two-step problem of list your variables, identify which one you're trying to find, which one doesn't matter, which 3 you know. Then go on to step 2, which is pick the equation that matches to that, isolate for the variable you're looking for, plug everything in, and summarize your answer. So I know that realistically, you could be writing like step 1, 2, 3, 4, 5, and all the way down, but let's just break it into step 1 and 2, and then summarize our answer. I think that might be the best way, because then when we get to our advanced problems, as we call them, you're going to see that we may just go 1, 2, 3, and then summarize this, an equation, and we'll be fine with this. All right, example number 3. Let's take another look. So again, it always starts with identifying the variables. So what I'm going to do is go step number 1. We have VI, we have VF, we have acceleration, we have the change in time, and we have change in displacement. Now, does the order in which these variables occur matter? No. You can put these in any order you want. I'm totally fine with you putting VI at the bottom and change of time at the top. That's totally fine. You just need to make sure you write out all 5. Now, in this example, we have the following. They say if a ball is thrown downwards at 15 meters per second, then the ball hits the ground 6.7 seconds after being thrown. What is the ball's vertical displacement? Okay, let's write down what we got here. So if the ball is thrown downwards, remember, thrown downwards means that VI is not equal to 0 anymore. And in fact, downwards is a negative velocity. If you need to write that in for yourself, point to this 15 meters per second and be like, this means it is a negative velocity. And so what I'm going to do is, instead of putting like just a positive 15 meters per second, I need to pay close attention. It's being thrown downwards. This is negative 15.0 meters per second. What is the final velocity? They didn't really say anything about that, so I'm going to assume that we don't need this for this problem. Acceleration, this is an implied thing. If it's in free fall, you have to know that as it's close to the surface of Earth, it has to be this negative 9.81 meters per second squared. If it was higher off the surface of Earth, it's a potential that it's less in magnitude. But what we want to do is just be like, hey, anything we're talking about, like throwing footballs or throwing rocks around or whatever it might be, as long as it's generally close to the Earth's surface, this will always be negative 9.81. The change in time was 6.70 meters per, or not meters per second, but just seconds. What is the displacement? That's our question mark. So as you can see, VF is that variable we don't care about because we've identified 3 that we knew, using assumptions as well, and then we now want to figure out what the displacement is. Now, there's only one equation that matches up to this, so for step number 2 here, we're going to put this together. Maybe I'll raise up number 2 just in case we need to do any algebra. It gives us a little more space. So we're going to write in displacement is equal to VIT plus 1/2 AT squared. All right, now the nice thing about choosing this equation, as you see, we're looking for displacement. We don't need to do any algebra with this. So we can go right to the numbers here, and that's exactly what we're gonna do. Displacement is equal to VI, which is negative 15.0 meters per second, multiplied by the time, which was 6.70 seconds, plus the 1/2 A, which in this case is the negative 9.81 meters per second squared, times the 6.70 seconds, and this is squared. Whew, that's a little tight, but we're gonna make it work there. Okay, so that's squared. Now this is gonna be equal to, and rather than forcing it there, let's just make sure that I'm gonna just erase this out, and we can actually just shuffle it over just very slightly, just so we're not condensing it in there and you can't see your answer. So this is gonna be 6.70 seconds all squared. There we go. Now, if you enter this into your calculator, again, what do we got to be thinking about? This object was being thrown down off a cliff, and so the end displacement should be negative or in the downwards direction. If you're not thinking that this is negative, then you're not getting these signs correct. So displacement is equal to, we're going to write this as negative 321, which could also be written as the following. We could also say that the displacement is equal to 321 meters in the downwards direction. This would also be a completely acceptable answer. And I'm even going to put in therefore, just to really show that we're summarizing an answer together. That's what we get. So either one, you just got to be prepared to see either one on an assessment there. And again, look at what we've seen out of these first 3 problems. We've seen some assumptions being put in here. We've seen that we've had to identify variables in their appropriate way of saying, hey, are they up or down? And then we've also had to do the 2-step solution of identify the variables, pick a formula, sub your answers in, and then simplify your solution. That's pretty typical with these ones here. Okay, now we're going to get into some more complex examples here. The more complex examples simply just expand upon our definitions and our understanding of these and say, hey, rather than them just being a simple 1-2 step solution, we now might have to be like, hey, let's solve for one variable and then solve for another, or let's break apart the problem into part 1 and part 2 and then put it together to give us the final answer. So let's take a look at how these look. Okay, a rock is being thrown upwards from a 20-meter high cliff. with an initial velocity of positive 35 meters per second. How long does it take the rock to hit the ground below? Okay, now this one is going to be a little bit interesting because we're going to introduce this idea that you can actually blend 20-1 material in here, but you have to be very, very, very careful with this. And we're going to go through this in class as well, because we need to make sure that you have a firm understanding of when the quadratic equation can be used and how it's used to get an answer here. Okay, so in the first case here, a rock is thrown upwards from this cliff. I would honestly just maybe even draw in a visual here, especially with this type of approach with it. I think drawing in the visual is really critical just to see what's happening. So here's our cliff. Here is the rock's trajectory. It gets thrown up and then off the cliff like this. Now I'm going to try and draw this just a little bit better, where we have it kind of going up and then back down. There we go. That's perfect. And then what I'm going to do is I'm going to draw in an axis that represents up is positive, down is negative. So we'll draw that in here neatly, where this is positive, this is negative. Excellent. And let's just make sure that's extended just a touch. Now, I'm going to also fill in the fact that they said the initial velocity was equal to positive 35 meters per second in the upwards direction. Okay, now the cliff, or the total displacement, let's back that, displacement is equal to negative 20.0 meters, because it's going down the cliff. In this type of problem, we're not throwing it onto the cliff, we're going down the cliff, so it has to go in the downwards direction. How long will it take for the rock to hit the ground below? Okay, now what I want us to do is I want us to list out the variables. So for part number 1, I'm going to create my list, VI, VF, making sure the tails are there. I got acceleration, change in time. I got my change in displacement. Perfect. And now I'm just going to put in all the values that I have. So thus far, I have the positive 35 meters per second, which is being thrown into the air off the cliff, or in the upwards direction. I then have my displacement, which was equal to negative 20.0 meters. I also have the acceleration, which is negative 9.81 meters per second squared, because remember, this is close to the Earth's surface, so we can continue to use that definition. What I don't have here is they say how long it takes to hit the ground. That's our question mark. VF so far, and here's what I'm going to caution you. So far, I would think that this is the variable we should be excluding, is this VF, because they didn't mention anything about it. And it's like, if they don't mention anything about it, you might be tempted just to write that one off. But I promise you that might not be the best way to do this. So based on the following criteria and based on the variables, I'm going to substitute the following. Number 2, if I saw this, I'd be like, okay, displacement is equal to the VI times T plus 1/2 AT squared. Now, here's where the issue comes up, and I really want you to highlight this in your notes. If I see a T here that's single, or it is degree 1, and then I see a degree 2 T, I will never be able to isolate this T. And so writing in below this, I'd be like, we need the quad formula. To isolate T. And I'll even put in brackets like that. And quad formula, if we look at this, it's because it's a quadratic. It's a quadratic function. And I'll even short form it as this: quadratic, fancy f of x, meaning quadratic function. Because if I looked at this, I would have eventually have to isolate it on one side. So maybe let's do that, but I don't really want to solve it in that way, and I'm going to explain why. So let's say we were to do that, and I wanted to make everything go to one side and then make it look like a quadratic. Here's what it would look like. Therefore, if I wanted to plug this as a quadratic function, it would be the following: 1/2 AT squared plus VIT minus the displacement is equal to 0. Because in order to make this into quadratic formula, or put it into quadratic formula, we have to have some sort of AX, BX, plus a C is equal to 0. And so in this case we do. What I might do is just multiply everything by the 2 to both sides, and that's going to allow me to get rid of that fraction. So when I multiply everything by 2, I get the following: acceleration times squared plus 2 times VIT minus 2D is equal to 0. Now, here's what I'm going to caution against. For some of you, you're like, oh, this is great. I got my AX squared, I got my BX, I got my c, and this is going to be equal to 0. Oh, that looks fantastic. I got my quadratic formula. I can type this in and just easily get a solution. Here is where I see the number one mistake come in. When you do quadratic formula, you're getting x-intercepts assuming that you're at the origin. But what do you notice about this problem? The quadratic is starting up here on the cliff. The quadratic ends here. And so if you do your x-intercepts and you do quadratic formula and get the x-intercept, you're actually including the time that it takes to go here and here. Because as we know, on this x-axis here, or on this very bottom portion here, represented by pink, that is the t-axis. And so if you include the x-intercepts, what you're doing is you're telling me the total amount of time it took to get from here to get to here. And you're including this section up here that we don't want. And so you have to be pretty on the ball with this one and say, okay, rather than just purely calculating for the x-intercept and then calling that my time it takes, you have to realize that you're starting at a position on the quadratic that is not the x-axis and you're somewhere else. And so the total amount of time is actually from the green dot to the green dot, which is shorter than just being a regular x-axis, including when you do these quadratic formulas, often your x-intercept on this side is 0. And so if you go from 0 to the green dot, you're saying that that is a time that it takes to go from there to there, but you're including a time that doesn't actually exist in this problem. So please be very careful with this. Okay, here's what I'm going to say about this. Rather than treating this as step number 2, we're going to say, hey, if you want to go this way, you could go this way. That is definitely an option. And so I'll even call it like, option I'm going to classify it as option number 2. I don't even want to make this option number 1. You could use quadratic formula if you have taken 20-1 and you're familiar with these tools. However, here's the way I would approach it. As a physics student, you should be approaching it in the following way. Let's try to figure out a variable that would allow us to solve not using the quadratic formula. And you know what that variable is? We need to solve for the final velocity. This is the key critical emphasis that we need to figure out in order to go forward with this and actually figure this out. So what we're going to do is on the next page, and if there isn't a next page, I'll make sure there's a next page, we're going to try and find the final velocity. And then once we know what the final velocity is, then what we can do is we can figure out the total time for this. Okay, so rather than treating quadratic formula step number 2, now what we're going to do is say, hey, once we've identified our variables and we want to solve for VF, let's solve for it. So to find VF, which is step number 2, we do the following. So finding VF, VF squared is equal to VI squared plus 2 times acceleration times the displacement. Because we know we have the height of the cliff, we have the initial velocity it's thrown upwards with, and we have the acceleration that's applied here. What we have to do from here is then square root both sides. So VF is equal to the square root of VI squared plus 2 times the acceleration times the distance. And I'll make sure that 2AD looks a little bit better. 2AD, there we go. And then I'm going to say VF is equal to, now I'm going to plug everything in based on what I was given. So first of all, we have positive 35.0 meters per second. This is squared plus 2 times the acceleration, which is negative 9.81 meters per second squared, multiplied by the negative 20 meters that represented the distance down the cliff. And it's really important you put that negative because the double negative is going to make this positive. Now VF is equal to the square root of, or maybe we can actually just type in the answer here, we should get the following, plus or minus 40.2 meters per second. Okay, now I want you to critically think about this. Here is the first case scenario of why, when we look at this equation, we do not put the vector symbols above. The reason we do not put the vector symbols above is if I know a square root can result in a positive and a minus, and I'll even include that in the note here. So if I know that this square root can lead to either a positive or a negative, then I need to be really astute with this and be like, okay, if this can result in a positive or a negative, now what I have to do is make a logical decision. What direction was this final velocity heading in? The final velocity was heading downwards in the negative direction. So our magnitude must be the negative answer, not the positive answer. This is that final velocity we actually really want. Now, in this equation, this isn't actually what we're solving for in the problem. We are just solving for final velocity to avoid using the quadratic formula. Now that we have this, let's find t. Step number 3 is going to be finding t now that we have VF. So find t. underline. There we go. Okay, here's our equation we're going to use. If we know acceleration, final velocity, initial velocity, and we're solving for the time, we're just going to use acceleration is equal to VF minus VI divided by the change in time. And I'll extend that just a little bit more. What I know about basic algebra is that if I multiply the time up to both sides, I'm eventually going to have to divide by the acceleration back down. So these end up swapping places. I'm going to get the change in time is equal to final velocity minus the initial velocity divided by the acceleration. There we go. Now, if I plug in the values I know here, I'm going to get change in time is equal to final velocity was the negative 40.2 meters per second minus the positive 35 meters it was thrown at, or in the upwards direction, divided by the acceleration, which was negative 9.81 meters per second squared. Therefore, the overall change in time was equal to, and I believe we get 7.67 seconds. There we go. So this gives us that perfect final answer in terms of making sure we get the right answer. And there we go. So rather than using quadratic formula, just be aware that we got to look at this and be like, we got to account that when I look back at that parabola on this page here, if I end up just treating this as the original position is 0, 0, and then my final velocity is the ending time, I'm going to get this wrong. And when I do my x-intercepts, it's going to give me the wrong value. So you just got to look at this and be aware that it might not account for the time you're actually specifically looking for, and we just got to be a little bit aware of this. But yes, you do have the ability to go either quadratic formula, or you have the ability to find another variable that you may have not known originally, and then use that variable to then solve for the variable you're looking for. And so this is where we say it can get maybe a little bit more complex, is you might have to solve for one variable before you've solved for the other. All right, example 5. It's going to be similar to that, but just maybe in a slightly different context. Here's the context that we are having in this problem. A car is traveling at a constant speed of 32.5 meters per second for 15 seconds. So as soon as I see the word constant speed, what I want you thinking is this is uniform motion. So I want you to point an arrow to this and say this is uniform motion, or UM. They've also given us a speed and a time. And so we have one interval that has a certain speed and a time, and we can calculate distance out of that. Then the vehicle uniformly slows and then comes to a stop in the 14 seconds. This is the accelerated motion component. And so I'm going to point an arrow down here and say this is accelerated motion, or AM. So if I have accelerated motion, now I have to use the equations we've established in lesson 5 and 6. Okay, we're going to break this into two intervals because there's constant speed and then there's something changing in this overall speed. So in the interval 2, or in the overall intervals, I want you to create a t-table where we have interval 1 here and we have interval 2 here. Under the constant speed, or the uniform motion section, what I want to do is say that the speed was 32.5 meters per second. The change in time was equal to 15.0 seconds. And then we're looking for how much distance did it cover in that area. And then for the part 2, we're going to do something very similar. We need to start by saying, okay, our VI is equal to, what I'm going to do is I'm actually going to say this is positive 32.5, just because they didn't establish any sort of direction with these. So I'm just going to say, hey, let's just make it by default positive. It says it comes to rest, so final velocity is 0 meters per second. The acceleration in this case, we actually don't know. And then in terms of the change in time, it takes place in 14 seconds, so 14.0 seconds. And then we're looking for the overall distance, or the displacement covered in that interval. Because here's what the problem is asking for in the very end. What is the total distance? We know distance is a scalar value. And so as soon as we see the scalar value, we just need to make sure that we total up the distances traveled, and that's good. Okay, so part number 1. Let's solve for the distance in the uniform section. We say speed is equal to distance over time. When I plug in the values here, the distance we actually are trying to isolate for, so I'm going to multiply up the t to both sides. So multiply by t, multiply by t. This is going to give me the following. I get distance is equal to speed times time. And when I plug it in, distance is equal to 32.5 meters per second multiplied by the time, which is 15.0 seconds. Okay, distance in interval 1 is equal to, and let me make sure I get the exact value here, we should get 47.5 meters. There we go. And I'm even going to classify it as that. Distance 1, distance 1, distance 1. There we go. Okay, and I'll highlight that just to include it. Now, before we get our final solution, we got to figure out how much distance was covered in the second interval. To do that, we're going to use a different equation, an accelerated motion equation. Distance, or the displacement, is equal to, in brackets, we're going to do the average velocity, or VI plus VF, divided by 2, multiplied by the change in time. Now, the nice thing is we don't need to reorganize this equation. We just got to plug in the values here. So D and D2 more specifically is equal to, the velocity was 32.5, I should say, because we start at 32. There we go. We add 0 because that was the final velocity, and we divide it by 2. Lastly, on the outside, we're going to multiply this by, just to get it right here, 14.0 seconds. There we go. Okay, now we put this together and we say D2 is equal to, well, this is averaging the velocities and multiplying by the overall time. I end up getting 227.5 meters. Okay, I'm going to highlight that. Now that we have the distances and displacements, displacement is just another way of saying distance in that one direction. And so unless this was an accelerated problem that like changed directions a bunch of times, which it doesn't, unless it changes a bunch of times, we're just going to consider that to be another distance. Now to get my final solution, I just do the following. Therefore, the total distance traveled is equal to D1 plus D2, or the accelerated motion section plus the uniform section. DT is therefore equal to, when I put these things together, I get a total of 715 meters. And the reason I don't have a decimal is because I need to make sure this has the proper amount of significant digits here. So that's my final answer here. So these are another popular type of question. You might see these in the work problems, is breaking things into different intervals based on the different types of motion and then combining them and get some type of final answer in the end here. All right, we got one more problem to go through, and it is the example 6 that deals with inclines. So what we want to do is, anytime we have an incline, these are extremely popular. I would star this as like a, hey, you're probably going to see these again. Like, you know, these are just really popular. They exist in forces. They exist in kinematics. They're all over the map. Like, they're everywhere. So you want to make sure you write this one down, or that you star this. Okay, a ball starting at 3 meters per second is rolled up the incline and comes to a stop in 5 meters. What is the velocity of the ball 8.6 seconds after starting up the incline? Now, what we're going to do is we're going to try and draw a detailed diagram off to the side that will help us gear how this problem should look. So I'm going to draw a right angle triangle representing an incline. Off to the side, what I want you to do is I want you to say that when we talk about inclines, positive is up the ramp, negative is down the ramp. Now, what you can include on this is we're going to put a ball at the bottom of the ramp and point an arrow going in the up direction, because the ball originally starts going up the ramp. Now, putting on some notation here, we said that from the problem, the VI is positive 3.00 meters per second because originally it's going up the incline. It then reaches, after 5 meters, some point on the ramp. So I'm going to draw the ball maybe like right here. And we're going to say that right about here, this is that point in which it transitions from positive velocity to negative velocity, or where the velocity final is equal to 0 meters per second. When does that happen? After a total displacement up the ramp of positive 5.00 meters. So you may want to make sure you write that in there. Okay, what is the velocity of the ball 8.6 seconds after starting up the incline? Now, the one thing you need to look at this problem and be a little skeptical of is, how do we know where it's going to be? Is it going to be going up the ramp, down the ramp? We actually don't know. And so when they say 8.6 seconds after starting up the incline, one thing that's missing in this problem that you need to recognize anytime you're dealing with these incline problems is the acceleration on the ramp. And so if you're not given acceleration, I would make sure you write this at the top. If you do not have acceleration, solve for it. Super critical, and I'm even going to highlight that in like blue right at the top. If you do not have the acceleration, you must solve for it. So my whole goal of starting this problem, because I don't know how the ball is changing in its overall velocity during this interval, I got to make sure I figure that out first. So step number one, just like we did before, apologies for that, skipping around. Step number one, just like we did before, is I'm going to list out the variables I know and I don't know and which ones I don't care about. So VF, VI, I have my acceleration, change in time, change in displacement. Equals, 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 and equals. There we go. Okay, so for my VI, this was positive 3.00 meters per second because it was going up the incline. The change in time, I mean, we don't really want to consider that right now. Right now, we're trying to solve for acceleration. We don't know how the acceleration plays into this overall timing, so leave that out for just a second. My final velocity is 0 meters per second. We're going to consider how this object interacts just purely going up the ramp for now. So consider us only treating this as kind of like a half problem for now, where we're like, hey, what is the acceleration as the ball goes from the bottom to the top, or to that 5 meter area? Acceleration, that's our question mark. We don't know that. The displacement is equal to positive 5.00 meters, or 5 meters up the ramp. Now you want to be thinking about which equation involves these such that we can solve for the final velocity, or not the final velocity, but the acceleration, I should say. And the equation that should come to mind would be this one here, part number 2. We're going to say VF squared is equal to VI squared plus 2 times the acceleration times the displacement. Now we want to solve this for acceleration, so I'm going to minus VI squared minus VI squared. This is going to give me VF squared minus VI squared is equal to 2 times the acceleration times the displacement. And now, in order to isolate this for the acceleration, we're going to divide by 2 times the displacement on both sides, 2 times the displacement, and this will give us an equation of the following. Acceleration is equal to VF squared minus VI squared divided by 2 times the displacement. Now, let's plug in the values here, and I'm just going to move this equation just slightly over so that I can make sure I can fit everything onto this page, and then we'll continue with the next step on the next. So my final velocity was 0 meters per second. It's where it came to a rest at the top of the ramp, or wherever it was after that 5 meters, minus the initial velocity, which was positive 3.00 meters per second, and this is squared on the outside, divided by 2 times the change in the distance, which was 5.00 meters, to get to where it came to a resting point. Now, even sliding this over just a little bit more, so maybe we can fit the answer right next to here before we go on to that second piece that we need to solve for. Acceleration is equal to this equation. We plug in our magnitudes, our directions, we plug in all the values, including their units. We should get that the following is true. Acceleration is equal to negative 0.9 meters per second squared. There we go. So this is the answer we get when we do this math here. Now, that means that the acceleration is always negative, no matter where we are in the ramp. And hopefully that makes sense to you based on our previous discussions, because we've said that when we talk about acceleration being negative on the ramp, it's because the object is always experiencing a downwards push due to gravity. And so there's some sort of overall force acting on this object, or some sort of overall opposing force on this object. And that opposing force is gravity acting against the ball in the downwards direction. And we'll specify that more when we get to things like forces, or even unit C, when we start really breaking it down of like what type of vectors are actually going against this thing. But for now, we're just going to say, hey, we know that the acceleration is constantly acting against this ball in the downwards direction. So it's negative 0.9 meters per second squared. Now, that wasn't our final answer. What we wanted to figure out was, what was the velocity 8.6 seconds after starting up the incline? So step number 1, we solve for this acceleration that was missing, that is critical to determine how our velocities are changing. Now for step number 3, in our more complex example, we're just going to solve for that time, or we're going to solve for that overall velocity in the ending position. So solve for VF. All right, now the equation that can do this for us is simply just our basic acceleration equation. And this is the reason why. If I go back to the variable list that I should look at, I can say we have VI, VF, acceleration, change in time, change in displacement. if I put the values for everything that matters here, now you're going to see that I've changed a little bit. Displacement no longer matters because 5 meters is no longer symbolic of where the ball is going to be after that 8 seconds. It was only to get to the top of the incline. So I'm not going to consider that. We then had a timing of 8.60 seconds. We have an acceleration that we just found of negative 0.9 meters per second squared. We have a final velocity of who knows, and then an original velocity of 3.00 meters per second. Now, the equation that would match up to this is our basic acceleration equation. We're going to say that acceleration is equal to the change in velocity over change in time. Another way of writing this is saying that we have VF minus VI divided by the change in time. Now, if I want to isolate this for acceleration, we're going to start by multiplying out change in time. So I multiply both sides of the equation by change in time. This gives me acceleration times change in time is equal to VF minus VI, and not VI squared, VI with the vector symbol. I'm going to add VI to both sides, add VI to both sides, and therefore I'm going to get the following. VF is equal to, now we have A times T plus VI. When I plug this all in, VF is equal to the acceleration, which was negative 9 or 0.9 meters per second squared. The time was 8.60 seconds. 8.60 seconds. There we go. And then plus our initial velocity, which was positive 3.00 meters per second. There we go, just to make sure it all fits in there. Therefore, our final velocity is equal to. Now, if you do the math on this, what you're actually going to find is that you get an answer of negative 4.74 meters per second. Now, for some of you, you might be like, that doesn't make sense. How do we get a velocity that is greater than our original velocity? And we're looking at this, and even if I flip back to the ramp here, I saw that as it started to roll up the ramp, or right when it was at the very bottom, this was positive 3. It declined in overall velocity into the point that it got to 0. It started coming back. And what you should realize is that at the very bottom of the ramp, and I could even throw this in maybe orange, at the bottom of the ramp, you would consider the final velocity equal to negative 3.00 meters per second. We have this nice symmetry when it comes to things that face this acceleration on a ramp. What this means is if I have negative 3.00 meters per second at the bottom of the ramp, this object is off the bottom of the ramp and has traveled even more distance past the ramp. So this means the ball is on the way down, first of all, and I'm even going to say it on the way downward, off the ramp, and it is traveling faster than the original position. Perfect. So, and then just to say this, you could be like, I guess I said off the ramp there just to make sure. But what you're looking at this is you're saying VF is negative because it's traveling down. It's going in the opposite direction to our original motion. And because it has some sort of overall magnitude that's greater than the bottom of the ramp, you know it must have traveled an additional amount of distance off the ramp after that 8.6 seconds. Because at the end of the day, the 8.6 seconds wasn't to get up to the 0 position. 8.6 seconds was to go up the ramp from the starting position, pause, come back down, and then go to somewhere off this ramp here. So in this kind of pen that I've highlighted over, that would be roughly about the journey that we face here, is that the ball would be somewhere off the ramp, or like somewhere off the ramp down at the bottom in the negative direction, or in the opposite direction as up the ramp. Okay, That does it for our examples. So what I would like you to do is start on the practice problems. The practice problems are going to be very critical for this section, especially when it comes to things that involve that quadratic formula one, where a rock is being thrown off a cliff and then it's landing down. You want to make sure that you can use the physics approach rather than the Math 20-1 approach. And then if you really want to, you could confirm your answer with the Math 20-1 approach, but it might catch you on that approach if you are not careful with your starting and your end. And then for ones like this final example here, just realizing that the ramps are a very critical problem as we move forward. And you might see more and more of these, especially as we introduce the dynamics section when we talk about forces. So just be aware that these are setting up a very important skill that we're going to carry forward here.